3 students, welcome back to physics lesson with me, Pratama. And today we are going to talk about one kind of wave, which is the sound wave. In this video, we are going to look at the factors that influence the speed of sound and how to measure it. Sound travels at about 340 meters per second in air at sea level at 20 degrees Celsius. What does this tell us? This tells us that the temperature and also air pressure will affect the speed of sound. Sound can travel through air, and at this, the speed of the sound changes again for different mediums. So how is this possible? It's all to do with particles. So sound travels about 340 meters per second in air. In water, it travels at 1,500 meters per second, while in some solids, sound can travel up to 5,000 meters per second. That is incredibly fast. Compared to air, these differences are due to how particles are arranged in solids, liquids, and also in gases. In solids, particles are fixed in rows touching each other. In liquids, particles remain touching each other for some gaps are present. And in gases, particles are far apart, occasionally colliding with each other. So, what's the relationship between distance of particles and also the speed of the sound? Pause the video and have a think for it. The closer the particles lie, the faster sound is able to travel. Sound waves travel faster through solid and liquids because their particles are closer together. So it's easier for the vibrations to hit the next particle. Another way of saying this is the more densely the particles are arranged, the faster sound travels. So now we can link this idea to how temperature affects the speed of sound in air. When temperature increases, the kinetic energy of particles also increases. In a gas, the particles collide more often at higher temperatures, passing on the vibrations. So sound can travel faster as the temperature of the gas increases. What about air pressure? At sea level, the air particles are more densely packed, and at altitude, this means at sea level, the vibrations of sound pass more quickly between the particles and sound travel faster. How does changing the speed of the wave affect frequency and also the wavelength of a wave? You should already know how to use the wave equations that we have studied last week. When the speed of sound changes as it enters a different medium, the frequency remains the same, but the wavelength will be changing. The frequency cannot change as it is set by the source of the sound. So, as speed increases, wavelength also increases. As the speed decreases, wavelength also decreases. For example, a sound wave moves from air to water, speeds up because the particles are closer together in the water than in the air. As the speed of the sound wave increases, so does the wavelength. Can you think of an easy experiment you could do to measure the speed of sound? Pause the video and have a think. Okay, one option is to get someone to stand exactly 400 meters away with a stopwatch. Make sure you can clearly see each other. When one of you bang a drum with your drumstick, your partner needs to start the clock when they see you hitting the drum and stops the clock stop when they hear the sound. Repeat this experiment a number of times, then take the average of all readings. We can now work out the speed using the equations speed equals distance over time. So speed equals 400 meters divided by 1.2, giving a speed of 333 meters per second, pretty close to 340 meters per second, but not exactly the same. Why do you think this is? Pause the video and have a think. Okay, it is maybe colder than 20 degrees Celsius, or maybe we are at higher altitude than sea level, or maybe it's a human error that stopwatch timer had slightly delayed reactions. So we've seen that the speed of sound wave varies between solids, liquids, and also gases, because of how closely or far apart molecules are for the vibrations to pass between. And also the atmospheric pressure and temperatures also affect the speed of the sound. Okay guys, that's all for today. We are going to talk about the resonance in sound wave, and I will do some demonstrations to show you the effect of resonance in our Zoom session. Thank you for your attention and bye bye.